talk of the workshop. And our presenter today will be Roch Guerin. So it's really a pleasure for me to introduce Roch. He's currently the chair of the Computer Science and Engineering Department at Washington University. And before that, he was a professor at the University of Pennsylvania after spending 12 years at IBM T.G. Watson Center. Interestingly, he first studied in France at INST before going to Caltech for master and PhD. So he got international recognition, mostly for his contribution to understanding the fundamentals of data network design and how networks can be designed to provide expected quality of service guarantees. So his work actually on this topic was among the earliest in the area, and is considered by the community as very important. He wrote 5 RFCs. He got SAM Fellow nomination and IEEE Fellow nomination. Recently, he was the keynote address at InfoComm 2021. But I understood that his talk today will be about much newer results that he recently obtained and that are going to be presented at the forthcoming symposium on edge computing next December. So Roch, please go ahead and start your presentation.
Merci, Sébastien. All right, let me share my screen. So let me try to figure. Share and all right, can you see the full screen?
Yes, very good.
Okay, all right. Sorry, I sometimes Zoom does pretty nasty things. It's running on a virtual machine and it doesn't, and PowerPoint doesn't like that. So, okay, thanks for the introduction. Apologize if I'm a little bit disjointed. One of the things I don't like about these remote workshops is that because you're remote, everybody who is, wherever you are is still expecting you to be here as opposed to there. And so you end up being somewhat with a split personality. And so I'm trying to adjust to Central European time and so what I'll talk about today is actually, as Sébastien was alluding to, somewhat recent work with several colleagues at WashU and students. And it deals with a problem of an edge computing problem, in particular in the area of classification. And I'll also make that a little bit more explicit in a second, but where the communications between the devices and the edge compute resources still are subject to some constraints. And in particular, they're regulated by means of a token bucket, which is obviously a pretty common way of doing things, right? So that's sort of a high-level picture of the kind of system where this kind of scenario would arise, right? So you can think of a conveyor belt, so some kind of distributed systems where you have to recognize and classify objects that belong to different categories. And take some actions once you've classified objects that belonging to a particular category. The devices that are doing that are detecting the objects are sort of, say in this particular example, cameras that are connected together by a network, and then there's an edge server that's available. Because of the distributed computations sort of, or the need to handle the load and do perform timely decisions, you try to do most of the classification decision on board on the cameras themselves. And as usual, right, the classification decision is typically in the form of a vector that tells you the probabilities of the object that you've just looked at being in a particular category. And if you determine that the chances that you're right are pretty low, and I'll make that a little bit more specific in a second, you may want to have a second opinion on whether you've detected the right object, and that would then involve sending the image to this edge server that has a much stronger classifier because it has access to much more powerful resources, but because either network or compute resources at the edge server are still bounded, are limited, and you do need timely decisions, there is a need for some form of regulation, and that's where the token buckets comes in. So, the cameras cannot offload every single image because that would overload either the network or the server, and the token bucket is going to realize that control, right? So that you're going to be limiting the number of images that can be offloaded to the server for a potentially more accurate classification. All right, so I mean that's sort of one particular example you would have, right? In terms of the kind of environment that where this could be deployed. The one thing that I want to sort of highlight here is we're going to, in order to actually sort of tackle this particular problem, we're going to represent both the token bucket in a somewhat discretized fashion, right? So we're going to assume that both the token rate, namely, so you need a token to offload one image, right? And so the rate at which you're getting token is therefore determining what fraction of your images you can offload to the server. And the bucket is there to give you some flexibility in possibly offloading, a couple of images back to back. So the rate is usually going to be less than 100%. So you cannot offload 100% of your images. You can offload, let's say, 5%, 10%. Those would be the kind of values that we would be looking at. But we're going to make the assumptions that both the rate and the bucket size are rational numbers, right? And so with that in mind, you can then represent the evolution of the token bucket using the equations that are represented on that slide, where the notation N of t is the number of tokens that you have, which could be a fraction of tokens, and A of t is the action, whether you offload or you don't offload. So 0 if you don't offload, 1 if you offload, and so this is just tracking, how many tokens that you have. All right, so now what is our classifier, right? So we have a set of, taking the images as our example, you have a set of images, so that's a continuous valued sort of input. You have a set of discrete classes, and we have a representative training set that is telling us, what's the odds of that images belong to different classes. And that sample is available to us, right? And so we have these two classifiers, which are making decisions whenever they get an image in terms of which category the image belongs to. The weak classifier runs on the cameras. The strong classifier runs on the server, right? And we have a loss function that's going to be dependent on the application. And so, for example, if you look at a top 5, right? So sort of application or sort of classification, what you want is that you want to make sure that the correct image is indeed in the top 5, right? And then your loss, therefore your error would be 0 if you're in the top 5 and 1 if you are actually not in the top 5, where top 5 is in terms of the top 5 categories that are listed in that probability vectors that I was referring to earlier. And so from the point of view of a camera that's trying to make a decision, there is a potential reward that's associated with whether or not you want to offload that image, which is a function of the difference in loss function that you have if you send it to the edge server or you just rely on your local result. All right, so our decisions, right, the actions that our camera is going to be taking depends on the input, so the image that it receives, that they come in at a certain rate, and the reward that's going to be associated on whether or not, depending on whether it offloads it, right? And so in the first part of the work, we're going to assume essentially periodic inputs. So your images are arriving at sort of regular time intervals, right? And they are i.i.d, so essentially you sample from the set of possible categories independently for every new event. And so once you've made those assumptions, and they are somewhat constraining, although they're applicable in some environments. Once we've made this, then basically the problem boils down to a Markov decision process. We're going to further assume that we want to sort of make, since we have cameras that are limited in terms of their capabilities, we want to keep the complexity of the policy that runs at the camera relatively low, and so we're going to be looking at threshold-based policies, right? So essentially, what we want to do is sort of maximize sort of some form of the reward that we're getting across all those cameras when they make offloading decisions subject to the constraints of the token bucket. Right? So what are some of the issues that we are facing? So the main issue is, how do I compute an offloading metric, right? So I've mentioned that we want to use a threshold, which is a function of the reward. If you're above that threshold, we offload you. If you're below that threshold, we don't offload you, right? But how is that threshold computed? Well, on the basis of what metric? Especially since when you get an image, right, the camera has the image, it has the output of the weak classifier, but that's it, right? I mean, and the reward is actually a function of the output of the strong classifiers, which clearly you don't know at that time, right? And so so the choice that what we picked was essentially a metric that's based on the function of the entropy of the weak classifier output. So if you look at the weak classifier output, as I mentioned, it's a distribution, right, of the odds that that particular image belongs to a particular category. And we're going to express our metric as a function of the entropy of the weak classifier, which is really the only thing that we have at our disposal, right? And so how do we connect this the entropy of the weak classifier to the reward, which depends on the strong classifier? This is where the training sample that I was referring to earlier comes into the picture, and we use a pretty standard formulation for essentially estimating using the entropy of the weak classifier, the expected reward that we are likely to get if we get an image that has a particular entropy value as produced by the output of the classifier, the weak classifier that runs in the camera. So that's sort of a pretty standard things. The one thing that I want to point out is, depending on the type of classifier that you have in the camera, entropy and reward need not be monotonically related, right? So, for example, if you have a weak classifier that is actually pretty decent running on the camera, you get the kind of outcome that you have on the left, right? So, what those figures are plotting is the purple quote unquote dots are all the instances of images that we get, and the reward that's actually associated with that image. So it's either 0 or -1 or 1, right? And this is using a top 5, right? So you get no reward if both of them make the same outcome. You get a reward of +1 if you make you improve things, and -1 otherwise, right? And so what you see in this particular case, right, is that when the entropy is very high, it means that it's an image that's really, really hard to classify. Actually, not both the weak and the strong classifier are sort of clueless, right? They're not able to come up with a good answer, and which is why as the entropy gets higher and higher, the reward function, the metric, goes down, is because these are actually images that are inherently hard for both classifiers to produce the right categorization. While on the right-hand side, you have actually a much weaker classifier running on the cameras. And in those cases, when the entropy is high, this is actually a reflection of the limitation of the classifier itself, rather than the fact that the images are really hard, right? And so, right, and the main reason I want to highlight this is that this is really something that you need, that's a calibration that is important, because depending on the type of classifier that you use on the local device, you can end up with sort of a different mapping between reward and the entropy of the images that you are classifying on the local device. All right. So how do I compute optimal threshold? I'm not going to go through that. It's actually pretty standard. It's a sort of a value iteration approach. There's a paper it's on arXiv, and so you can obviously check it out. It's a sort of a pretty standard techniques. And so let me jump into the evaluation. And so we looked at 3 configuration. One which is a single device, and we're going to focus on that one device and try to do the best possible thing for that device. But the more interesting thing is that when you have multiple devices and they're all running, they're all being controlled, right, or regulated, but what you're interested in is the overall performance of the entire system. And there we're going to actually look at 3 sub-configuration. One where we just manage each device individually, independent of the other. The other one where we're actually going to manage the devices, quote unquote, semi-jointly. And I'll explain that in a second. And the third is where we actually have a smart switch where, the devices, as they arrive, right, are first connected to a switch that is applying not only regulation to the aggregate of all the communication from the devices, but is also capable of making intelligent decision in terms of which images to offload and which not to offload. So in this last category, right, what the individual cameras would do their classification, but would always offload the image. That those images would arrive at a switch together with the result of the weak classifier, and the switch then would use both pieces of information, the image and the result of the weak classifier from that particular device, to decide whether or not it should be sending it up. So it's implementing both a token bucket and essentially the policy that we are talking about. And we're going to be essentially using the ImageNet sort of benchmark to evaluate our policy and compare the performance to a couple of other sort of alternatives, simple alternatives, right? And so one alternative is going to be what I call a naive policy, right, which basically says that if your token rate is such that you can offload 10% of your images, I'm going to be looking based on my training set at the top 10% of the metrics, the offloading metrics, and any image that's above that 10% threshold, I'll offload. Any image that's not, I will not offload, and that's going to be independent of the token bucket constraints. The other one, the lower bound, is essentially the same policy, but now assuming that you have an infinite token bucket, right? So the problem with the naive policy is depending on whether or not you have a token, or how many tokens you have, you could actually be a little bit more or should be a little bit less aggressive, right? So if I'm about to essentially overflow my bucket, my token bucket, then rather than losing the tokens or a fraction of a token, I might be better off sending an image, even though that image has a relatively low metric, right? The reward may not be very high because in any case, I would be wasting or nearly, some amount of tokens. If you have an infinite token pool, that problem doesn't arise. And so the naive policy under the assumption of an infinite token pool is, pretty much as good as you can do. All right, so looking at the top 5 error, this is basically showing you, the y-axis is the final error that that you end up with in your system, and so lower is better. So as expected, the strong classifier gives you better performance, a lower error than the weak classifier. These are the 2 dotted lines, right? And in between, what you have are different configuration, where on the x-axis we vary the token rate. So obviously, the higher the token rate, the more images you can offload, and the closer we get to the performance of the strong classifier. And the different colors correspond to different bucket depths, right? And so again, the lower bound corresponds to an infinite bucket depth. And the one thing that's interesting is that with a relatively small bucket, 305, you actually get pretty close to that. So now, how does if I focus on a particular slice, namely a particular rate value, and so here I've picked 10%, so you can offload on average 10% of your images. Here, what we're comparing is our policy, which is sort of the solution of that NDP, to this naive baseline, which is basically doesn't care about the state of the token bucket, versus the MDP policy that tries to actually adjust its decisions based on how many tokens you actually have, and then compare that to the lower bound, which is again this infinite bucket depth, which is basically no, I mean, you don't really have as strong of a constraint, right? And so what we see is that there is some improvement. It's arguably not huge, but it's nevertheless some level of improvement. Now, the interesting thing is to actually see what does the policy do, right? Just to sort of dissect a little bit, sort of the behavior, what is captured, and sort of try to see if it confirms our intuition that as you get more tokens, you tend to be a little bit more aggressive in the decision that the policy is making. Given that none of those policies is as perfect hindsight, right? They don't really know whether the next image is going to be an image that would really benefit from being offloaded, but you've just run out of tokens. It only relies on the statistics that have been available in the training set, right? So on the left-hand side, we vary the token rate. And what we're plotting is the fraction of images that are offloaded. And so the straight line, right, would be basically what we should achieve, or what we would achieve if we had an infinite token pool, right? So you would be able to essentially offload exactly all the images that you're entitled to offloading. You would never have an issue where you want to offload an image, or you had a token, but you did not use it, and therefore you've ended up offloading fewer images that you're entitled to. And we see that's actually what happens, right? The interesting thing is, the NDP policy is actually a little bit, so which is the full lines versus the naive policy, which is the dotted line. The NDP policy is actually when the token rate is it is actually lower than the naive policy for sort of different values of the token rate and bucket depth. So in particular, when the bucket is small, let's say b equals 1, it means you can only have one token. That's the least that you need, right? We can see that's actually lower when the rate is high. And the reason is that, well, it is actually higher when the rate is low, right? And when the rate is low, right, it actually has a lower threshold, right, than the naive policy, is because it knows that it should get rid of that, or it should spend that token very quickly, because it takes a relatively long time to accumulate, again, a full token, which is what you need in order to send the images. While when the rate is high, right, it ends up actually being more conservative, because it really knows that it should be spending that token on sort of images that are really worth it. And since the rate is now high, the cost of not spending that token right away, since it doesn't take as long to replenish it, is now lower. And when we look at the right-hand side, which is now, instead of varying the rate, we're varying we're looking at the decision as the number of tokens that are available varies, right? We actually see sort of in some sense the variable threshold behavior of the policy, the more tokens you have, right? And so we have 5 sort of lines, or 4 plus 1 lines that correspond to different bucket depths, right? So if you look at the one on the right, the rightmost one, which is the brown colored, which corresponds to a bucket of 5, then depending on how many tokens you have, you can see that the metric that the policy decides to pick for which image to offload starts dropping, right? The more buckets, the more tokens you have in your bucket, the more aggressive you are willing to be, which is again intuitive and what we would be expecting. And this is actually what produces the improvement that we've seen in the previous slide. One question that we were interested in is what happened if our training set is messed up, right? So which is sort of not an uncommon thing with in many systems. And we wanted to understand how sensitive the policies would be. And so this is sort of results where we've removed or we've therefore made the training set inaccurate by removing a certain percentage of images in the metric range of images from our data, either 10% of the images or 25% of the images, and we've removed either the bottom, namely images with the lowest metric, or the top, namely images with the highest metric. And we see that when we remove the bottom ones, the MTP policy is actually relatively unaffected, even when we remove 25% of the data, which is the right-hand side, which is not totally surprising. It's because, even though we've trained it with a set of images that had, obviously, therefore, sort of conditionally higher metrics, the ones we've removed are images that it would anyhow not have sent because they are very low metric, right? While the naive policy is actually much more affected by that because it's not making adaptive decisions. Now, when you remove the top sort of metrics data, then I think both policies are more affected, and that's again because it biases all the threshold. It puts them to a much lower value than they should be, and therefore both policies end up making somewhat inaccurate decisions. All right, so moving on to the multi-device extensions, right? As I said, we have 3 configurations. So one of them is basically, extending what we've just done. So each device has its own token bucket, and that determines whether that device can send or not based on the local policy. Configuration 2 is each device has its own token bucket and makes the decisions according to whatever the policy is telling it to do. But now there is an additional rate control that is applied at the sort of the aggregation point where you have multiple devices that are coming onto the network, right? So you can think of you have a whole bunch of access points that are all feeding into a whole bunch of devices that are feeding into the same access point, and that access point is running its own aggregate token bucket, which is controlling all the input from all the devices. And what that opens up, right, is the ability to actually slightly over provisions the token buckets of the individual devices. It's not clear up front whether or not that's going to be beneficial, so that's what we're going to be looking at. Because the token bucket at the aggregation point is going to still make sure that whatever gets sent into the network conforms to the traffic envelope that we want to limit the transmissions to, right? And the third one is what I think I described a little bit earlier. There's no token buckets in the devices. They all do their classification, and they all send their image plus the result of their own local classification. And then the switch, the access point, does implement an aggregate token bucket, namely aggregate on all the devices, and uses the results of the local classification of the individual devices to actually run our policy. So it's not doing the classification, but it's implementing the policy, which is relatively simple to do. Right? So the advantage is it's essentially equivalent to the single device policy, but now run at this aggregation point. And so, this is, shows that the results for a bunch of different configurations where, we vary the number of cameras, the number of devices that are aggregated together. So the blue line is going to be the individual devices. We run, a token bucket and our decision policy at each device. The green line represents the quote unquote smart switch that makes policy decision using the classification information from individual devices plus the token bucket that apply to the aggregate. And the orange line corresponds to this intermediate step where the devices have actually making the policy decision, but we've actually configured them with slightly over provisioned token bucket, where the over provisioning is configured in a way that is actually the optimal over provisioning, where the optimality is obtained by basically an exhaustive search of all the configurations through basically emulation of the system. Now, how does that over provisioning look like? right? And so what we see here is that the over-provisioning scheme is actually relatively good at getting close to what would be, quote unquote, the best we could do, which is having this smart switch, right? And this is showing, how the over-provisioning looks like, and it's sort of a heat map, which the yellow, sort of or warmer colors means higher, and performance, better performance. And so in this particular case, the best performance is associated with a pure yellow color, right? Because that's the thing that corresponds to the minimum color. And what we can see is actually that in some configuration, it is actually useful to over provision the individual token buckets in both rate and bucket depth. So, right, so let's suppose that you have 10 cameras and you have a rate of 10%, right? So that would mean that each camera now normally would get a rate of 1%, and you have a bucket size of 10, which means each camera would get a bucket size of 1, so that the aggregate still satisfy the aggregate rate of 10% and a bucket size of 10. And so instead of now allocating just the 1/10 of the rate and the bucket size to each camera, we can actually allocate them a little bit more, right? And how much more is the over provisioning that I was referring to. And here, what it shows is that in some configuration, over provisioning on both rate and bucket depths benefits you, right? So allowing the devices to be a little bit more aggressive is beneficial. On the rate side, that's because if you remember, right, our policy ended up being slightly conservative, not fully utilizing its full token rate. And so this is, it's sort of intuitive that if you're not fully utilizing your full token rate, it's okay to over provision because it's not going to harm you. On the bucket size, it's all in some sense because it allows you to recapture some of the statistical multiplexing gain that you're losing. Right? So if you have devices that are now giving a small token bucket, basically they have, the advantage of the bucket is that it allows you to, smoothen out fluctuations in the classification decision that you're making. And if you making the token bucket very small, you're losing that sort of averaging opportunity, which you can now recapture to some extent if you are over provisioning. And what we see is in our particular scenario is that we can actually over provision quite a bit without much harm, right? And there's actually additional explanation in the paper as to why that's going to be the case. Right? Time-wise, how much more time do I have?
Sorry, maybe 5 more minutes.
Okay, all right. So I'll have to zoom through the second part. Basically, what I just wanted to sort of highlight here is that sort of we looked at an edge computing or edge classification scenario, provided an MVP formulation. It, however, had and we could demonstrate that with that particular policy, we could improve or we could produce some meaningful improvement in terms of the quality of the classification decisions, in terms of deciding what should be sent to this edge server towards improving the accuracy of classification. The solution was, however, obtained under quite a few assumptions. In particular, we assume that images arrive periodically, and that images where essentially the classification accuracy was drawn from an underlying distribution and with no dependencies, right? That's often not true in practice, right? So your images may not arrive nicely and regularly. You could have bursts of images and then nothing for a while, and then another burst of images. And same thing for the classification decision, right? Let's say lighting condition change so that there's a period of time during which the quality, the accuracy of your classification decision is relatively low, and then lighting condition improve, or you get a bunch of objects of a particular type that are inherently harder to classify. You get a bunch of them in a row, and again, so there could be correlation in how classification decisions are structured. And so that's basically what we wanted to target. and we couldn't really do by just simply extending our Markov decision solution. And so what we did, and it was actually one of my first exposure to reinforcement learning, and it's I'll sort of it's somewhat of an acquired taste, and I've not fully acquired it yet, but it is actually a pretty powerful sort of type of solution techniques. And in this particular scenario, it worked remarkably well in allowing us to actually extend or build a solution that could handle a much more complex configuration, right? So namely a configuration where we could have sort of basically arbitrary arrival patterns, right, which would be hard to represent using sort of a simple arrival process, and an arbitrary correlation in the classification decision or in the structure of the classification decision of the images that were being produced, right? And so, as I said, we used sort of a reinforcement learning solution called Deep Q Network, DQN, that has been actually pretty popular and was successfully used in a number of sort of relatively high profile. I think the Atari game being the first place where it was sort of demonstrated, and it the reason it was sort of appealing is that it's able to handle a much larger state space than just the token bucket and the sort of image, the structure that we had in the Markov decision process. And if you have a complex arrival process, complex correlation, right away, obviously the state space that your policy has to consider sort of blows up, right? And a deep Q network is essentially a tool that would allow you to handle that much higher dimensionality. And so, given that we don't have much time, I'm going to sort of skip over this and sort of basically very quickly go through some of the results that we were able to obtain using that particular system. And we looked at sort of three sort of scenarios, right? One where there was variability in the arrival process of images. One where, but we kept the assumption that classification decisions were i.i.d, and so they were sampled, from an existing distribution, which we knew, but we were sampled independently in every, successive images. The second scenario is we flip that around, right? We keep the periodic arrival, so images continue arriving nice and regularly, but now there is correlation in the classification output, so you can add whatever structure you want in terms of, whether you have a bunch of images that are hard to classify, followed by a bunch that are easy to classify, so you can create arbitrary correlation structures. And the third one is putting things together, right? And what I want to actually just jump to, so the bottom line is that you do better than if you ignore, if you have, you're basically, we compared this to what we would do if we had a solution such as the MVP solution that we had developed that was basically oblivious to either the correlation in the classification output or in the fact that the arrival process did not have a constant rate, right? And basically, the net is this reinforcement learning approach was able to actually do better across the board. The more interesting thing is to sort of look at actually what is that reinforcement learning sort of policy doing. And so these are actually traces, and I find them actually a little bit more illuminating than sort of just trying to just look at the performance improvement. So this is assuming that you have images that arrive regularly. So this is our first scenario, right? So you have regular images that arrive, but the output of the classifier, right? The type of images that you get has some correlation. And here the correlation structure is you can get sequences of images that are within a range of metrics. So you could get a bunch of images that are relatively easy to classify, followed by a bunch of images that are a little bit harder to classify. So we create some correlation in the output process. So that's essentially, if you look at the y-axis, right, the metrics, that plots the metric, right? The width of the bands that we have on those two plots are basically representative of the correlation that you have, right? So if there was no correlation, they would span the entire range from 0 to close to 1, right? And so what we see actually is that the fact that the DQN solution is aware of that correlation structure leads it to making quite different decisions, right? And in particular, we've color-coded the decision, and blue are images that get offloaded by DQN, while orange is offloaded by both, and there's a typo here. The red is actually offloaded by the MDP, right? And so what we see is that the DQN policy realizes that it may be stuck in a regime where you're going to have a bunch of images with a relatively low metric, and it decides to then, yep, I'm stuck in that bad state, but if I don't do anything, I'm going to lose tokens. And so it knows, it has learned that that correlation structure is present, and it's therefore adapts its decision to this, and that's in turn allows it to produce better results. We can do the same thing, right? So this is another similar trace where you now have a change in the arrival rate, right? And so on the right-hand side of that line that's in the middle, we switch to a lower arrival rate, while on the left-hand side, it's a higher arrival rate. And so actually in both cases, right, the policy, the DQN policy knows that, it is in a region, so on the left-hand side of higher than normal arrival rate. And so it knows that, it can expect images to arrive faster. So it needs to be a little bit more conservative in how it's spending its token, while on the right-hand side, it knows that it has a lower arrival rate, and therefore images are going to be further apart, and it ends up being actually less conservative and a little bit more aggressive. This is why we see some blue, low metric images that get offloaded, while the other policy doesn't do that, right? That gets mitigated when you increase the bucket size, right? So as can be expected, and that's what the bottom figure is showing you. And you can actually do the same thing when you put everything together, and that was of interest to us because we wanted to make sure that the DQN structure was able to learn both the arrival process and the correlation structure in the classification decision. And I think I'm out of time, right? Or do I have a few more minutes? So this is basically representing a trace that has the result of a DQN policy. And in order to tease out whether or not it's learned both the input structure and the classification structure, we've trained it in two different ways. We've trained it in one way where it's unaware of the output structure, and in the other way where it is, but it knows about the input structure. And the other training is training where it is aware of both the input and the output structure. And the trace is illustrating that when it knows about both, it's actually adapting its decisions in a way that indeed indicate that it has learned both aspects, right? So in some sense, it's a validation of the fact that the learning, did take place, and that learning is actually translating into policy decisions that we can sort of rationalize, and that are in turn are responsible for the better improvement that I don't have them here, right? That we are able to see when we use the DQN policy. So I'm stop here, right? So I think the one sort of thing that I wanted to convey is, even though I'm still not particularly keen on reinforcement learning, it is actually a very powerful tool. It allowed us to actually extend and design a system that implemented a policy that it could improve the classification performance of our system in the presence of a much more complex environment, which was therefore a much closer to the kind of environments that you can expect to see in practice, and produce sort of improvements that we would not have been able to realize if we had tried to use a more standard sort of approach, such as the MDP approach that we use in our initial system. And I'll stop here.
All right, thank you very much. Is there any question in the audience?
Yes, maybe can I ask a question?
Yes, please go ahead.
Yes. In my understanding, the weak classifier and the strong classifier are trained separately. Is it correct?
I mean, they've been trained on the same data set.
But separately. Okay. So,
but right, because I mean, they have different structure, right? So they're not, they're, you know, they obviously.
But on the other hand, they are coupled together because they work in conjunction. They work together. They are working together. So I was wondering whether there has been research in the literature trying to couple the two training together,
right,
for the weak classifier to understand easily if, okay, I'm not able to classify this image. So I train the weak classifier in order for it to realize adding some more neurons and another decision instead of just classifying the images. I can also understand if I am able to classify the image or not, which may be a problem that is easier than object classification itself, so that I can understand, okay, I will send this type of images with this structure to the strong classifier.
Right, so I think that's a good point. That's a good question. Yes, there's been work in trying to essentially jointly train two classifiers towards achieving a common goal, right? And that's not what we've assumed here, right? We assume that, you know, we basically had off-the-shelf classifiers that were, you know, each of them were independent. Yes, they were trained on the same data set because they were going to try to achieve the same outcome, but they were basically you know, they were not jointly designed. These were not things that we were fully controlling. We were just taking off-the-shelf components, training them for our particular application, and then with these two pieces in place, try to figure out how to, assuming that they were then given to us, how do we best use them? But you're absolutely right that there is definitely another setting where, you know, if you control the entire ecosystem, you could certainly envision that you would want to jointly train those two classifiers towards achieving an overall goal, right? That, however, assumes that you have actually, you know, you can specify and you can control all these individual pieces. The assumption that we had is that, you know, we did not own the entire system, and we had to, even though we were assuming that you know, each piece of that system was indeed trained to perform, you know, whatever perform adequately for the classification task, given the data set that was available. We did not have any ownership of what individual pieces of technology were going to be used in both the devices and the edge server.
Okay, thanks.
Another question, sorry? No? Actually, I have one question. So when you start to get something distributed, in many cases, you will eventually have to take into account the possibility of malicious behaviors. So in your case, the strong classifier should be managed and monitored, so it shouldn't be malicious, but the weak classifiers, if they are run on phones, there is always the possibility that the code is altered and that it could try to fool the strong classifier afterwards. So in your scheme, I had the impression that the random process of selecting which one was a good proposal or bad proposal, and also the scheme of over-provisioning somehow could mitigate such behaviors too. Does it make sense to you?
So, so let me see. So if I look at the over-provisioning scenario, right? So this is a scenario where you have a bunch of devices that are feeding a common access point, right? And the common access point is the one enforcing access constraints, right? Namely, the fact that it's from that point onward, you're not going to be violating the amount of traffic, right? Now, you're right that in the case of the this oversubscription, right? So the oversubscription would not harm the rest of the system, but it could you could certainly, if you have one or more misbehaving device within that group that gets aggregated together, right? If one of them misbehaves, namely decides to send every one of its images, for example, right, which is the worst case, that the worst sort of behavior that you could have, that would potentially affect the other devices that are part of the of its own group, right? It's somewhat mitigated, right? But yeah, so we haven't looked at the, so what I would expect is, right, if you think about it, if now you have one device that oversubscribes, so if actually you look at, right, oops, this picture, right? So oversubscription and rate is increasing the y-axis, right? And so you're going to obviously be limited in terms of what one device does, but if you have one device that is really sending every one of its images, right, that corresponds to a high oversubscription rate on the y-axis, which results in a dark blue sort of outcome, which is indeed a much lower sort of a higher error rate for that particular group, right? Yeah, there's not much that we can do, right? The smart switch, right, would provide some mitigation to that, but then you could argue that in the smart switch case, the local device could still fool the smart switch by sending an incorrect classification output that says, oh, this is a very high metric, such that, right? And so yes, barring additional security measures, there's going to be exposures of that type.
Thank you. Any other question from the audience? All right. Well, I think that concludes the last scientific talk of the workshop. So thank you very much, Roch, for the workshop. So in